Hello everyone, welcome back to Physics 425. We're gonna kind of change gears now, and what I'd like to do is I'd like to spend the remaining time in the course trying to understand some of the theoretical aspects of superfluid helium-4. And in order to do that, what we first need is some background in statistical mechanics. And so the next, probably 4 or so videos will be focused on kind of reviewing some of the fundamentals of statistical mechanics, and then we will apply some of those results to try to further our understanding of superfluid helium-4. Okay. And so some of this might be a review, but that's okay. The first thing we're going to talk about is the statistical mechanics interpretation of entropy. And so here's the core idea. Well, maybe multiple ideas. First, what we're going to try to do is specify the state of a system as completely as possible. So that means what we might do is identify the position, momentum, energy, spin, and so on of each particle in the system. And then for each of the possible states of this system, we'll call that a quantum state or a microstate. So call each possible state of the system a quantum state or microstate. Okay, so next we're going to imagine an ensemble of systems. And so these are a collection of systems that are identically prepared. So imagine an ensemble of systems that are identically prepared. So you might be thinking of like a closed jar of some kind of gas. So you have a whole bunch of these jars. Jars are all the same volume. They all contain the same kind of gas and the same number of these gas particles. They're all at the same temperature and all of these things. So they're all identically prepared. So same number of particles at the same system energy. They exist in an environment with the same electric and magnetic field, and so on, all the other conditions that you can specify. So for this ensemble of systems, there is a large number of quantum states that are consistent with these conditions. So if we look at each one of our jars containing the same type of gas with the same number of gas particles, and they're all at the same temperature with the same internal energy and all these things, that doesn't mean every single particle in each of the jars is in the same position. Like, all the particles can be in different positions, which corresponds to different microstates. Each of the individual particles will have their own individual momentum that aren't the same in each of the jars, and so those all correspond to different types of microstates. And all of these different microstates are consistent with a jar of gas at a fixed volume and a fixed pressure at the same temperature, and all of these things. Okay. So this ensemble is called the Microcanonical ensemble. And what we'll do in our little review of statistical mechanics is we're going to come up with, we're going to think about different types of ensembles. And so this first one is the microcanonical ensemble. Okay. So if there are, say, W possible quantum states, that satisfy the constraints on energy, volume, particle number, and so on. And so think of our jars, like if we had Avogadro's number of gas particles in our jar, the number of different quantum states would be absolutely enormous, like almost even impossible to imagine how many different combinations of particle positions and momenta are consistent with the constraints on the energy and volume and particle number and those types of things. So it's an absolutely huge number. So if we have W of these quantum states, then we're going to assume that all quantum states are equally likely. That is, the probability of going to one of our jars and finding it in a particular quantum state is just 1 over all of the possible quantum states. So the probability of being in any particular quantum state is 1 over W. So let's just do a simple example for a small system. So let's take n equal 4 spins with 2 spin up with energy, say E up, and 2 spin down with E down. Okay, and so in order to satisfy our constraint on energy, we must have 2 spin up and 2 spin down. So what we could do is we could count the number of different arrangements of the system. So if we need n particles, and we're going to have to choose n of them up, and then capital N minus n up is the number of particles down, like so. So for our case, it would be 4 factorial over 2 spin up factorial and 2 spin down factorial, which would be what? 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. And so that's going to be 12 divided by 2 is 6. So there's 6 possible arrangements of the spins that satisfy 2 spin up and 2 spin down. And we could draw them for the small number of spins. So if we had 4 spins lined up, we could have the first 2 spin up and the second 2 spin down. Or we could have up, down, or up, down, and then we'd have to have down, up. or we could have the first spin always down, and so we could go down, up, up, down, down, up, down, up, and the last one would be down, down, up, up. And so those are the 4 possible cases. And so we have W equals 6 different microstates with n equals 4 spins and an energy equal to 2 spin up plus 2 spin down. And so we assume each state is equally likely, so that the probability of being in any one of these states is 1 over W, which is 1 over 6. And so that means if you had like 6,000 copies of this 4-spin system and they all had the same energy, 2 spin up, 2 spin down, then when you examined each of these 6,000 states, 1,000 times you'd find each of, on average, 1,000 times you'd find each of these 6 possible arrangements. Okay. So that's the first fundamental idea, is that for identically prepared systems, each of the available quantum states is equally likely. The next thing we're going to talk about is Boltzmann's hypothesis. So what Boltzmann's hypothesis is that the entropy of a system is related to the probability of being in a quantum state. So S is a function of W, the number of available states. Okay, so let's just take Boltzmann's hypothesis at face value for now, and then maybe we'll come back and think about whether that makes sense or not. But before we do that, this next argument that we're going to present is actually due to Einstein. So the next argument follows that of Einstein. And I should double check, but I think this argument was from 1905, and you may know that 1905 is the miracle year. So Einstein's miracle year. And why do they call it his miracle year? It's because in 1905 he published 4 revolutionary papers. One of them explained the photoelectric effect. Another one was a description or a theoretical understanding of Brownian motion. A third was his theory of special relativity. And the other one was this link between energy and matter. And so in addition to all of that, if I'm correct about the year, he also had time to present the following argument, which was not even part of what's known as his miracle year. Anyways, let's consider 2 independent systems. We'll have, say, system A and system B. And in addition to these independent systems A and B, we'll consider the composite system of A and B. as well as the composite system AB. Okay, so we also have this red system that includes A and B. Okay, well, according to Boltzmann's hypothesis, the entropy of system A is some function of the number of microstates of A. And the entropy of B is the same function of the number of microstates of system B, while the entropy of system AB is again the same function of the number of microstates of the composite system. So for two independent systems, the total combined entropy is just going to be the sum of the two. So if we had a composite system, the entropy of that composite system is going to be the entropy of system A plus the entropy of system B. Okay, for A and B independent, the total number of quantum states or microstates of system AB is, I claim, just the product of the number of microstates of A and the number of microstates of B. I think we can demonstrate that for a small number of states. And so let's say the states of system A is, maybe it has 4 possible states. And the states of B have, say, 3 possible states. Well, then the combined system, our composite system AB, it could be A in state 1 and B in state 1, or A in 1 and B in 2, A in 1, B in 3. Or it could be A in 2, B in 1, 2, 2, 2, 3. Or system A could be in state 3, and system B can be in any one of its states. And finally, A could be in state 4, and B could be in 1, 2, or 3. And so if you count the number of lines which determine the state of the composite system, there's 12 of those lines. And so in this case, WA is 4, and WB is 3, and the composite system is 12. And so 4 times 3 is the 12. Okay. So the number of microstates of the composite system is the product of the microstates of the individual systems. And so then if we go to Boltzmann's hypothesis, it must be that the entropy is some function of WAB, which then is some function of WA times WB. And what we want to do now is, why does that keep going away? Now we have 2 expressions for the entropy of the composite system. It's the sum of the entropy of the individual systems, or it's the function of the product of the microstates of the individual systems. Okay, and so that means that it must be true then that if we set these two expressions for the same entropy equal to each other, then we must have to satisfy this condition. And so we have to find some function phi, which, when it acts on the products of WA and WB, is equal to the function of WA plus the function of WB. And you may recognize this function. It's the ln function. And so the only solution is phi of W is some constant, which is going to turn out to be Boltzmann's constant, times the ln of W. And so that's easy to verify. We could take phi of WA, WB, and so if phi has to be this ln function, then we have some constant KB, ln of WA, WB, and for phi of A, we just get KB ln WA, phi of WB is KB ln of WB. Okay, and so that means that if we take the sum of the entropy of system A and the entropy of system B, that's going to be KB ln, let's start with A. B is Boltzmann. KB ln of WA plus KB ln of WB. But of course, if you have the sum of lns, that's equal to the ln of the products. And so this is equal to KB ln WA WB, which is equal to phi WA WB as required. Okay, and so that works. So with this interpretation of entropy then, we have entropy is defined to be KB ln of W. Of course, KB is Boltzmann's constant. Okay, so now let's go back and see if this result makes sense. So does this result make sense? I mean, really what it's saying is that when there is a large number of microstates available, then the entropy is large. And when W is small, a small number of microstates, then the entropy is small. So let's try a simple example. So let's do the n equals 4 case of spins, but this time let's require our system energy to be the energy of 4 spin-ups. So all the spins have to be up. And of course there's only one arrangement of 4 spin-up spins, and all 4 of them just have to be pointing up. And so there's only one microstate. Only one possible quantum state consistent with E equal to 4 spin up and n equals 4. Okay, and so that means in this case W is equal to 1 and S is KB ln of W, or ln of 1. Ln of 1 is 0. And so for a perfectly ordered system, the entropy is 0. And so that's what we expect. For an ordered state, we expect 0 entropy. For a perfectly disordered state S is equal to 0. Okay, so let's try a different example. N equals 4 and E is equal to 2 spin up plus 2 spin down energies. All right, so we already looked at this case. So we already saw that there were 6 microstates, and so therefore entropy is KB ln of W, or ln of 6. And at least compared to the entropy of 0 for our ordered state on the left, this KB ln 6 is comparatively large. And so this is comparatively large entropy for this more disordered state. So the summary then is that lots of available quantum states leads to a high entropy. And that's really what the Boltzmann hypothesis is telling us. Okay, I'm going to stop here, another short video, but next time we're going to look at another ensemble, and instead of the microcanonical ensemble, it will be the canonical ensemble. All right, thanks very much, and I will talk to you next time.